In OpenGL, the first programmable shader stage of the graphics pipeline is the Vertex shader. In the last episode, we already modified it, adding a uniform variable in order to unstretch the drawing. It means that when we called GLDrawElements and the Vertex shader was executed on the GPU for each chunk of data sent through the Vertex buffer, its output, which is the GLPosition variable, was not the initial data we sent through the Vertex buffer, but a transformed version of it. We performed a vertex transformation, which is the subject of this video, modifying data related to vertices, specifically its output position from the Vertex shader. In other words, changing the appearance of a shape by changing the position of each of its vertices. Matrices are the data type most commonly sent to GPU hardware to move vertices. First of all, because today's hardware supports and optimizes the use of matrices in shaders. That is to say, there are types representing matrices in GLSL, such as Mat3 or Mat4. Secondly, because the way they work mathematically enables us to change vertices positions seamlessly. So, what is a matrix? It is a rectangular grid of values with rows and columns. They are a way of holding values together, and here's what we need to know about them. A matrix with only one row or one column is respectively a row vector or a column vector. A square matrix is a matrix with the same number of rows and columns. They are the only ones we'll use now. A matrix can be multiplied with another matrix or a vector, respectively producing another matrix or another vector, and each value of the resulting matrix or vector will be the dot product of the corresponding row of the left member and the corresponding column of the right member. The product of matrices is not commutative. The result of AB can be different from the result of BA. The product of matrices is associative. Multiplying the result of AB by C will yield the same result as multiplying A by the result of BC. An identity matrix is a square matrix with ones in the top left bottom right diagonal and zeros everywhere else. Multiplying any matrix or vector X with the identity matrix will result in X. Now, how can we modify the position of vertices with matrices? In the Vertex shader, we can represent the initial position of the vertex as a vector of 4 components, x, y, z, and w. X, y, and z define the position of the vertex in space for each axis, and w is the homogeneous coordinate, generally 1. It is used for projection. More about the homogeneous coordinates in the article by Songo-An in the description. We can then multiply this vector with the matrices built to apply a specific transformation to the position of the vertex. After transformation, the vertices for which all 3 space coordinates are between -1 and 1 will have the points, lines, or triangles they represent be colored in the fragment shader and seen in the viewport. The others will be cold and won't be seen. In order to create these matrices and send them to shaders, we could use existing crates like GLM, which would probably be a bit more optimized, but we can also implement matrices ourselves to better understand. Let's do this instead. Create another file, transform.rs, which will contain matrices implementation. In here, create a public struct, mat3, that simply contains an array of 9 floats, the 9 values of a 3x3 matrix. Derive this struct with represent C to make sure the inside array keeps the same memory layout as a C array, which is expected by GLSL. A mat3 is enough for 2D transformations, but a mat4 will be necessary for most 3D transformations. Create a constructor method for mat3 that returns the identity matrix, so that the matrix applies no transformation to the position vector by default. Add a pointer method to get the row pointer of the matrix, which is the same as a row pointer to its first value. Another core method will be the multiplication of matrices. It will modify the current matrix, multiplying it with another one, resulting in a chaining of both transformations. However, let's say I want the position vector to be the rightmost member of the GLSL transformation product. This means, in order to transform the vector with the B matrix, then with the C matrix, I need the result of this multiplication to be CB instead of BC, as B must be the closest to the vector to be multiplied first, which will be on the right in this case. In the method code, we can simply swap the occurrences of self and mat to achieve this. Then on to matrices which will actually transform the vertex position. There are three essential transformations that enable a surface or model through each of its vertices to be manipulated in almost every way when chained. They are scaling, rotating, and translating or moving. First, scaling. It will multiply self with another matrix that scales a vertex relative to the center of the viewport, 0, 0. We have the ability to provide a different scale for each axis, so add one parameter for each axis. And that's it for scaling. These 9 values are the scaling matrix itself. Multiplying self to this chains whatever transformation was present in self with a scaling transformation of the user's choice. The same goes for rotation, which takes in an angle in radians and rotates the vertex clockwise around the center, and translation, which takes in x and y and adds them to its current x and y positions. The matrix containing these 3 transformations and derived transformations is usually called the model matrix. From main.rs, we can now create a model matrix and modify it for transformations. Let's keep an identity matrix for now to check it doesn't change from when we stopped in the last episode. Great, we now have an identity matrix available to be sent. Create a new uniform for it, uModelMatrix. Transfer the data of our matrix to shaders by calling gl uniform matrix 3fv. The first parameter is the uniform location we are storing as id. The second one is the count. We are only sending one matrix, so write 1. The third parameter is whether or not to transpose the matrix. Transposing a matrix means flipping it over its diagonal, which has the effect of swapping rows and columns. The first row becomes the first column, same goes for the second, etc. OpenGL happens to expect matrices to be column major, which represents values of the matrix contiguously column by column in memory. However, our mat3 is an array, thus the data we're sending is row major, so we actually need to transpose our matrix when sending it by setting this parameter to true. The fourth parameter is an actual pointer to the matrix, which we can get with the earlier pointer method. Now declare this uniform in GLSL with uniform mat3 uModelMatrix and multiply it with vec3 containing the position vector and a 1 to apply the transformation. Keep the unstretching after this multiplication, as it should be the last transformation for it to work properly. And finally, cargo run, and it should look like the last episode. You can try different transformations to check it works as expected, but mostly, to make it nicer to watch, you can update it every frame with an expression that depends on time to make it travel through the window. Here are some examples. One cool thing with organizing our code this way is that we can easily add a functionality we want, which you probably want when building an engine. For example, let's say I want to add a new complex transformation that is rotating around a specific point. Once I understand how I can do this from several existing transformations, which you can try to do by pausing the video now, I can simply create a function that will modify self by calling existing functions in a specific order with specific arguments. To rotate around a point with xy coordinates, I can first translate by -x -y, so the rotation center is moved to 0, 0, then perform a simple rotation, then translate back by xy. To check if this works, call the method and run. Once we're here, going 3D isn't that hard. The difference is that there's a third coordinate, z, which could be initially chosen in our program and sent with the x and y coordinates in the vertex buffer as long as we update the VAO accordingly. Instead, I will keep all vertices initially on the xy plane, that is to say with a depth value of 0, but create new transformation matrices that will also modify the z value. This is when we start using mat4 instead of mat3. While the mat3 transformation matrices could modify a vector of 3 values, among which the last stays 1, so can actually modify 2 coordinates, a mat4 can modify 3 coordinates in a vec4. We can copy-paste the struct and implementation of mat3 and modify it for mat4. Every array we work with now has 16 values instead of 9. Update every dot product of the multiplication for 4x4 matrix multiplication. For transformations, the same principle as mat3 applies. Multiply self with a new matrix that adds a transformation to self. Scale and translate methods can now take in a third argument for z, in the diagonal for scale, and on the right for translate. There are now 3 possible rotations, one around each axis. The previous rotation was implicitly around the z-axis. Move the sines and cosines to other entries of the matrix to rotate around the other 2 axes. Note that the earlier transformations for mat3 are included in what's possible to do with mat4. In main.rs, change the model matrix to a mat4 and consequently the uniform function of OpenGL to GL uniform matrix 4FV. And in the vertex shader, update the uniform to a mat4, multiply it this time with a vec4 containing the position, a 0 as the base z coordinate, and a 1 for the homogeneous coordinate. And we can simply send the resulting vector after unstretching to GL position. We can test a few transformations, like rotating around the x and y axis. Remember that vertices must be between -1 and 1 on each axis to be seen, so translating our shape in the foreground or background could either cut it or completely make it disappear. Nice. In 3D space, however, there are other transformations we can add that are often core features of an engine. Starting with a camera. In OpenGL, cameras don't actually exist, but we can create transformation matrices that will have the same effect as manipulating a camera in space. We can use the same struct mat4 for the view matrix as well. We can create several functions with a similar goal, positioning and rotating the camera. The maths of how this works is explained in an article linked in the description. To make sure the camera transformation is effectively happening after the model transformation, which is most likely wanted, we can create another matrix called view matrix with its own uniform and only multiply it with the already transformed vector inside the vertex shader. We can try rotating the shape around the z-axis while orbiting around. Orbiting can be achieved by constantly looking at the target position 0, 0, 0 while updating the eye position in a circle, giving the sine and the cosine of time to the x and z positions of the eye. we can also add projection to the scene. The goal is to project every vertex that is in 3D space to the 2D screen. Every vertex in space that's inside what's called the frustum will end up visible on the screen. The frustum goes from -1 to 1 on each axis. Just like with the camera, we cannot actually change the frustum, but transformation matrices can transform vertices such that the desired 3D frustum is mapped to the OpenGL frustum. There are two main types of projection we can add to Mat4. Orthographic projection, where the frustum is a rectangular parallelepiped, and all vertices are projected parallel to each other, perpendicular to the screen plane. And perspective projection, where the frustum is opened up and the farther items look smaller. This is the closest to eye vision. Each of these functions takes in a float for left, right, bottom, top, near, and far planes position on their respective axes. The maths of these two methods is also explained in an article linked in the description, which also has great visualizations for those interested. Similarly to the view matrix, create another variable, projection matrix, with its corresponding uniform, which you declare in the vertex shader and multiply after the model and view transformations. Orthographic projection seems to be the same as earlier, but it enables us to change the distance of each plane. If I change the x and y limits, the result is zoomed out. If I change the z limits, I can avoid shapes disappearing or being cut as well. For the perspective projection, you can choose the FOV or field of view, which is the angle you can see horizontally or vertically. A nearer or larger near screen will cause a bigger FOV, while a further or smaller near screen will tend to resemble an orthographic projection. Multiplying model, view, and projection matrices in this order is very common in 3D games. It even has a name, the MVP matrix for model view projection matrix. As a summary, the final combination brings vertices from local or object coordinates to world coordinates with the model matrix, to view or eye coordinates with the view matrix, to clip coordinates with the projection matrix, before OpenGL automatically takes the vertices that are in the -1, 1 frustum to window coordinates to be later seen on the screen. This is not the end, though. So far, we've only had one shape, or one model, so a single model matrix was enough. However, model matrices are meant to move objects in space independently from others, so each model can be placed correctly without moving every other one. First, we need a way to transfer several, and probably many model matrices to the vertex shader. This can be achieved with a uniform array, which is very fast to access from shaders, but has a fairly limited storage capacity, which we can determine by calling glGetIntegerV with the glMaxUniformLocations token. The returned value is the number of bytes which can be sent globally as uniforms, in my case about 4000, which will be way enough for what I want to do. Other solutions for bigger storage would be to use a Uniform Buffer Object UBO or Shader Storage Buffer Object SSBO. By the way, passing matrices directly through the vertex buffer could work too, but would eat up a lot of memory, plus 64 bytes for each vertex, and there would be many duplicate matrices since many vertices can form a single entity. Secondly, we need a way to choose which matrix of the uniform array to multiply each vertex with. As this is per vertex data, we can simply send an entity ID field in the vertex buffer. I call entity any group of vertices forming a single shape. These vertices won't move freely of each other, and there will be a single model matrix for all these vertices, so the shape is kept as is. Until now, we've only sent float numbers through the vertex buffer, so a vec of f32 was enough. However, it would be better if the entity ID was an integer, as that would avoid casting a float to an int when indexing the uniform array. That would also reach a wider integer range. In another file, create a new struct, Vertex, derived with represent-c for an OpenGL compatible memory layout. This struct will contain all attributes of a single input vertex, so for us, a U32 entity ID and a position which is an array of 2 floats. It will be the data layout inside the vertex buffer. Add a simple constructor that can be called with x and y positions. We can have a default entity ID of 0, which will be changed later on as it is a public field. In objects.rs, modify the VBO implementation to take in a vec of vertex instances instead of F32s, and modify the VAO layout to one unsigned int followed by 2 floats. The next time we modify the vertex struct, we'll only have to modify the VAO layout and the vertex shader, and it will work directly. In main.rs, modify the triangleFan function to return an array with instances of this new struct instead of floats as well. We can create another function, triangleFan3D, that will call triangleFan and will duplicate the shape entities number -1 times, updating the entity ID of vertices, and adding indices to the indices vec for the vertices of the duplicate shapes to be drawn. The duplicate shapes will all have the same position as the first triangleFan for now, but this will be changed if we use different model matrices for each of them. In the main function, replace the calls to triangleFan to calls to triangleFan3D with a given number of entities, like 6. Change the model matrix variable to an array of 6 mat4s. Transform each of them in a loop similarly, but with a unique transformation at the end that depends on the index, like a rotation around the x-axis. We can keep a single uniform for all model matrices as they are next to each other in an array, but we need to change the count parameter of GL uniform matrix 4FV to 6 as we are sending 6 contiguous matrices. Finally, in the vertex shader, we can put everything together. Change the declaration of UModel matrix to an array of length 6. Change the input data layout. At location 0 is the entity ID, an unsigned integer, and at location 1 is the position, a vector of 2 floats. Where we multiplied by UModel matrix, multiply instead by the element of UModel matrix at index entity ID. We can now try running. We can see a 3D shape, which means we've successfully performed a different transformation for each triangleFan. However, as everything has the same color, it's hard to distinguish each shape. To fix this, let's give a different color to vertices. As this is a per vertex operation, we could add a field to the vertex struct containing color data. However, there's a simpler way to color vertices as we don't necessarily need predefined colors. We can define the color of a vertex by its position data. For the nicest results, we may choose the vertex position after the model transformation. If we chose the initial position, many vertices of different shapes would have the exact same color, and if we chose the color after the view or projection transformation, the colors wouldn't rotate while the shapes would. So we chose a color for our vertex. We now need to transfer it to the fragment shader, which is a later shader which goal is to color shapes. To do this, we will declare a struct containing the color with the out keyword. This will send the struct to the next programmable shader, which is the fragment shader. We will receive this struct in the fragment shader with the int keyword and change the output of the fragment shader to this color. The color we send from the vertex shader is per vertex, and the color we receive in the fragment shader is per fragment. This is because between the two shaders, there's a process called rasterization, which breaks down each primitive, here triangles, into fragments. The data which is sent from the vertex shader to the fragment shader is interpolated, so every fragment has its own data, which is a mix of the data that was sent through the 3 vertices of the triangle it is inside of. Interpolation of colors produce smooth gradients. We will also divide the vertex color with the radius of the shape, so the gradient is never too short nor too long. Now we can clearly see that each entity is tilted relative to its neighbors. However, we still cannot stop there. There are some basic issues that happen when we enter 3D that we need to tackle. We can see some surfaces hiding others that should be closer to us. OpenGL can solve this for us if we use a depth buffer. Along the rasterization stage, it determines for each fragment which of the shapes that overlap on that fragment are farther or closer to the viewer, in order to represent the farthest before the closest, so the farthest is seen behind the closest. To enable it, call GL enable with the GL depth test token once, and GL clear GL depth buffer bit every frame before drawing. And this fixes it. Enabling a feature like this slows down the drawing process, so you should disable it with GL disable when it is not needed anymore. Another thing we may want to enable is color blending, so that partially transparent objects do not hide what was already drawn behind them. Again, call GL enable, this time with the GL blend token. We also need to specify the blending function in the equation. The blend function tells for all fragments how much of the source color already here and the destination color, which we are adding, will be present after the blending of the 2 colors. A common mix is source alpha for the source color and 1 minus source alpha for the destination color. I will stay with this. The blend equation defines the operation between the 2 colors. Adding is the operation we need to display transparent objects. Modify the opacity of the fragment shader output, and now it looks great! As a final note, I will say that working with computer graphics has a big advantage. Once you're set up globally, bugs are beautiful.